Good afternoon and welcome to this year's Henry Russell Awards program and lecture. This is a very special event in the university's calendar. One day we honor a colleague with the highest distinction this institution can bestow, the Russell Lectureship. The 2018 Henry Russell Lecturer is Professor Terry Robinson, whom Professor Schlissel will introduce to you shortly. I will share with you the history about the namesake for the Russell Award. Henry Russell earned 3 degrees from the University of Michigan, a Bachelor of Arts degree in 1873, a law degree in 1875, and then a Master of Arts degree in 1876. Russell was born in Detroit and remained in Michigan after graduation, where he was a successful lawyer and prosperous businessman. He was involved in companies such as the Michigan Central Railroad, the Michigan State Telephone Company, the Union Trust Company, People's State Bank, and the Detroit Steel Products Company. He was the type of entrepreneurial graduate of the University of Michigan who helps our state to thrive. In February of 1920, while in New York City, Russell took ill and died at age 67 from pneumonia, just as he was preparing to travel to Europe to claim his son's body. His son, Lieutenant William Russell, was killed in aerial combat in World War I. In his will, Henry Russell left the University of Michigan a $10,000 bequest to create an endowment fund. His one stipulation was that the income from the endowment would be used for additional compensation to members of the instructional staff. In May of 1925, the Regents established the Henry Russell Lecture as a way to recognize a senior member of the faculty with an honorarium of $250 funded by Russell's endowment. In addition, $250 was dedicated for an additional award to honor a faculty member below the rank of professor for conspicuous service to the university. Although the funds from Russell's bequest have long ago run out, the university continues to honor its most accomplished faculty with this award in his name. I am honored to be involved in today's ceremony to recognize these outstanding faculty members. And with that, I would like to invite Provost Filbert to present the Henry Russell Awards to 4 faculty members.
I'd like to invite Professor Justin Casper to come forward while I read the citation. Space scientist Justin Casper, a University of Michigan faculty member since 2013, designed spacecraft sensors to explore extreme environments from the solar corona to the icy moons of other planets. He is also known for his advances in space weather forecasting and understanding the solar atmosphere and solar wind. Professor Casper is principal investigator for the $72 million solar wind electrons, alphas, and protons investigation known as SWEEP, which will provide the first direct measurements of the properties of the solar atmosphere. He also is the lead scientist on instruments on the Wind and Deep Space Climate Observatory spacecraft, which have increased the advance warning times of solar storms. Solar flares and storms can damage satellites and degrade global positioning systems, communications equipment, and power grids. An inspiring teacher, Professor Casper gives students responsible roles in fabricating and calibrating instruments, thus allowing them to participate in the entire process of bringing a space mission from concept to launch. He has served on top-level NASA, National Academy of Sciences, and National Research Council committees, and is a member of the Michigan Institute for Research in Astrophysics and on their steering committee. Among other accolades, Professor Casper has received the Presidential Early Career Award for Scientists and Engineers and is the Smithsonian's Secretary's Award for Excellence. And the Smithsonian Secretary's Award for Excellence. Professor Casper, in recognition of your exceptional achievements in space science, teaching, and service, the University of Michigan presents you the Henry Russell Award. Will Professor Becky Lawrence Peterson please join me at the lectern? Electrical engineer Becky Peterson's advances in oxide semiconductor-based power electronics, solution-processed electronic materials and sensors, and nanofabrication techniques have important applications in renewable energy, healthcare, cybersecurity, and other industries. Among other contributions, Professor Peterson, a University of Michigan faculty member since 2009, has devised environmentally friendly, low-cost, and air-stable methods to fabricate flexible electronic skins comprised of thin-film electronic devices and sensors. She also is working on semiconductor devices that can operate at high voltages in harsh environments, including electronic and hybrid vehicles and oil and gas drilling operations. An innovative teacher, Professor Peterson uses industry-leading device simulation software and blind grading on exams to ensure all students have an equal chance of success. She also participates in outreach events for K-12 learners. Professor Peterson helped modify her department's faculty search process to ensure it seeks candidates from diverse backgrounds, and she works to recruit more women and Americans to its doctoral programs. She is co-principal investigator on a National Science Foundation Major Research Instrumentation Award to purchase a new scanning electron microscope for the University of Michigan. Professor Peterson has been recognized with the Faculty Early Career Development Award, the Defense Advanced Research Projects Agency Young Faculty Award, and the University of Michigan's Elizabeth C. Crosby Research Award, amongst other honors. Professor Peterson, in recognition of your contribution to next-generation materials, devices, and circuits, and your teaching and service, the University of Michigan presents you the Henry Russel Award. Will Professor Daniel Hrabowski please join me at the lectern? Biodiversity scientist Daniel Hrabowski combines mathematical and computer models of evolutionary dynamics, theories from evolutionary biology and ecology, and field-based research to study biological diversity over space and time. A University of Michigan faculty member since 2012, Professor Hrabowski created the Bayesian analysis of macroevolutionary mixtures, a computer program that quantifies heterogeneity in evolutionary rates. He has used this and other software developed by his group to study evolutionary dynamics in birds, lizards, bats, and other taxa. An engaging teacher and mentor, Professor Hrabowski involves his students in the Museum of Zoology's collections-based research. He is active in museum outreach programs and has expanded the use of UM's amphibian and reptile collection for education and research. He and his colleagues have added 2,500 specimens to the collection and have discovered new species of lizards from Australia's deserts. Professor Hrabowski is a member of the university's Council for Disability Concerns and has served on the Biological Sciences Building Planning Committee. In 2014, he won the Packard Fellowship for Science and Engineering, which recognizes the most promising young scientists from the nation's top 50 universities. He also received the Society of Systematic Biologists Ernst Mayr Award and the American Society of Naturalists Young Investigator Prize, amongst other honors. Professor Hrabowski, in recognition of your many contributions to evolutionary ecology, your teaching, and your service, the University of Michigan presents you the Henry Russel Award. Will Professor Paul Zimmerman please join me at the lectern? Computational chemist Paul Zimmerman, a University of Michigan faculty member since 2012, is known for his innovative research at the intersection of physical, materials, and organic chemistry, computer science, and applied mathematics. Amongst other contributions, he developed algorithms that predictively map multi-step chemical reaction mechanisms using novel quantum chemical methods. Previously, scientists had to guess the intermediates along a complex chemical reaction path. His advances allow chemists to more quickly design and test compounds for use in pharmaceuticals and in other fields. His group developed the first materials system using 2-electron storage for direct solar to chemical energy storage, leading to a new class of solar energy harvesting and storage materials. A creative teacher, Professor Zimmerman transformed the discussion section of his physical chemistry class into a sustainability-focused workshop, culminating in student presentations on topics such as green chemistry and renewable energy. He also supports the student-led Chemistry Professional Development Organization and undergraduate chapter of the American Chemical Society. Professor Zimmerman is a member of the Energy Institute and serves on the Michigan Institute for Computational Discovery and Engineering Steering Committee. Among other honors, he received the Faculty Early Career Development Award and the American Chemical Society Emerging Technologies in Computational Chemistry Award. Professor Zimmerman, in recognition of your pioneering contributions to computational chemistry, your teaching, and your service, the University of Michigan is pleased to present you the Henry Russel Award. And now President Mark Schlissel will present the 2018 Henry Russel Lecturer.
Good afternoon, everybody. I now invite Professor Terry Robinson to come forward while I read his citation. Behavioral neuroscientist Terry Robinson is renowned for his path-breaking research on the effects of addictive drugs on the brain, including the persistent psychological and neurobiological consequences of repeated psychostimulant drug use and the implications for addiction and relapse. Among other contributions, he discovered the brain mechanisms by which normal reward-related processes go awry, contributing to drug addiction. Professor Robinson, a University of Michigan faculty member since 1978, and one of the most highly cited scientists in neuroscience, has demonstrated that drugs of abuse can produce changes in the brain that linger long after the last drug experience and may become permanent. These effects can render the dopamine reward system persistently hyperresponsive to drugs and drug cues, contributing to relapse. An outstanding teacher and mentor, Professor Robinson spearheaded development of U of M's undergraduate major in brain, behavior, and cognitive science. He also directed the National Institute on Drug Abuse training program in neuroscience at U of M for over 20 years. Professor Robinson is past president of the European Behavioral Pharmacology Society, a fellow of the American Association for the Advancement of Science, and a charter fellow of the American Psychological Society. He edited the journal Behavioral Brain Research for 13 years. Among other accolades, he received the American Psychological Association Award for Distinguished Scientific Contributions, the American Psychological Society William James Fellow Award for Lifetime Achievement, and an honorary doctorate from the University at Lethbridge. Professor Robinson, in recognition of your many contributions to addiction neuroscience, teaching, and service, the University of Michigan is honored to present you with the Henry Russel Lectureship. I've even lost my place. I now invite Professor Robinson to deliver the Henry Russel Lecture entitled Rush to Reductionism, Lessons from the Studies of Neurobiology of Addiction.
Thank you very much for this award. Thank you for the introduction, President Schlissel. Thank you to the Award Selection Committee for selecting me. It is, of course, I'm a great honor, and I'm really thrilled to have this opportunity to talk to you today about a few lessons I've learned over the last couple years having to do with studies on the neurobiology of addiction. And the first thing I probably should do is just say a couple of words why I added this phrase, rush to reductionism, in the title. And I did so because I wanted to highlight a few points made in this opinion piece that was published last year in Neuron that actually also got a lot of popular attention. There's a very large, long article in The Atlantic based on the comments in this paper. And they point out that, I mean, what's special about the brain is that the brain produces behavior and psychological function. And insofar as the major goal of neuroscience is to explain how the brain does that, that is to explain how the brain produces some aspect of behavior, they argue that behavioral research must be considered, for the most part, the prior. That is, before we study the mechanisms by which neural cells and circuits produce behavior and produce psychological function, you have to first investigate the behavior or psychological function that you're trying to explain. And they point out here that even though that step is probably critical in neuroscience, it tends to be somewhat marginalized. I think they're actually overstating that a little bit. But anybody who works in behavioral neuroscience has got a grant review or a review on a paper that looks something like this. This is a paper of ours that's actually still under review. And it's a paper that's looking at the psychological mechanisms that are involved in the reconsolidation of memories. But the editors, rejecting the paper outright, aren't interested in the behavioral phenomena. But if we had novel cellular and circuit mechanisms that explain the behavioral phenomena that we're trying to describe, then it might be okay. And that's sort of the problem in a sense. That is, it's putting the cart before the horse. And I'm going to argue, based on studies from the neurobiology and psychology of addiction, that we do tend to put the cart before the horse and give the behavioral side of things short shrift sometimes. Not all the time, but sometimes. Now, in studies on the neurobiology of addiction, I would argue that the rush to reductionism often looks something like this. That is, you'll have a diagram of some intracellular signaling cascades, and this particular signaling cascade, if you read the caption at the top, says that it's a signaling cascade in a specific brain region, the nucleus accumbens, that results in psychostimulant addiction. And this will be familiar to anyone in the field. Now, drugs of abuse do influence these kinds of signaling cascades, but for this cascade to represent a signaling cascade that results in psychostimulant addiction, one would assume that the studies were based on some sort of animal model of addiction. But of course they're not. They're based on the actions of drugs of abuse, but they're not based on what you would think of as a model of addiction. And I will argue today that it's actually not even clear what we know what such a model should look like. Now, in modeling addiction, I'm going to argue that one of the critical questions we have is, why is it that the relatively few people who try drugs go on to have problematic patterns of drug use? That is, most of us at some point in our time are exposed to potentially addictive drugs. But it's a very, very small proportion of people that go on to have problems that we would associate with addiction. So what is it that makes some individuals resilient and some individuals vulnerable? And I would argue further that this is a very difficult question to address in humans, if not impossible to address in humans. And one reason for that is, although there are many studies on brain-behavior relations in human addicts, one problem is those studies are typically done after people have used drugs for decades, for 10, 20 years. And it may be that the nature of brain-behavior relations in such people tells us relatively little about how the brain got them to be that way in the first place. That is, how they made the transition to addiction. And I think, therefore, the choice of preclinical model that's used for studying this transition, how drugs change the brain to lead to addiction, becomes particularly important because one can ask questions of causality using animal models in ways that you simply can't in humans. Now, to paraphrase the statistician George Block, of course, all models are wrong, but some models are useful. And so these are going to be models. And so I'm just going to briefly describe what are the major preclinical models of addiction. Now, in the preclinical addiction field, the main model or procedure that's used to study the effects of drugs on brain and behavior involves drug self-administration procedures. So with these kinds of procedures, you'll put an animal into an operant chamber. This isn't working anymore. Well, yeah. And hook it up with an intravenous catheter. And when it makes some action, like press a lever, a pump turns on and gives it an IV injection of drug. And if you set that up, what you'll find is that animals will self-administer essentially all drugs that people will self-administer, with some interesting exceptions that I won't go into. I'd also like just a little Michigan connection here. The very first use or description, successful use or description of this drug self-administration procedure was in this science paper in 1962 by Jim Weeks, who at the time was working for Upjohn at Kalamazoo. So Michigan is where self-administration comes from. Now, of course, so there's been lots of studies on drug self-administration, lots of studies on the neural systems that mediate the reinforcing, rewarding effects of drugs. But everyone in the field also agrees that mere self-administration of a drug is not addiction. As I said, most of us self-administer a potentially addictive drug at some point, but most of us don't become addicted. And so that leads to a question in a preclinical model: how do you tell when a rat became addicted? That is, when did the rat make a transition from what you might think of as recreational, casual patterns of drug use to patterns of drug use that you would consider addiction? And there are ways that this is done in the field, and probably the most common one is highlighted in this paper that came from a group in Bordeaux a number of years ago, in which they looked at, on the left, the Diagnostic and Statistical Manual criteria from psychiatry for defining addiction, which is basically a checklist, and depending on how many checks you get, you are moderately or severely addicted. And then ask, can we measure some of these features that are on the DSM criteria in animals? And indeed you can. So in self-administering animals, you can measure things like continued drug seeking when the drug is not available, continued drug seeking despite an adverse consequence for taking drug. Is there a progressive increase in the motivation, the willingness of animals to work to get drug? Is there a high propensity to relapse after a period of abstinence? Is there escalation of drug intake? And you can measure all of those behaviors in animals that are self-administering drug, and you can measure how they change across experience with self-administered drug. And in this particular paper, when they allowed animals to self-administer drug for very long periods of time, they found that only a very small proportion, about 17% in this, met what they then called 3 criteria for addiction. That is, most of the animals didn't meet criteria for addiction. A small proportion did. Presumably, drugs changed the brain in those susceptible individuals in ways that drugs didn't change the brain in the non-susceptible individuals, or they brought susceptibility with them to the situation in the first place, which is another a whole set of literature. So probably today, the most widely used animal self-administration model that's considered a model of addiction is this one that was introduced by Serge Ahmed and George Koob back in 1998. And in their paper, in their science paper, they only focused on one symptom of addiction, escalation of intake. And what they did was compare 2 groups of animals. One group they called short access, that were put into the box and allowed to self-administer cocaine in this case for 1 to 2 hours a day. At the time, almost all self-administration studies were done under short access conditions because you could ask or answer what questions you had with 1 or 2 hour sessions. What they did was a little different, is they compared the short access animals to a group of animals given long access. And they were simply just allowed to self-administer for 6 hours a day. Of course, the animals given access to drug for 6 hours a day took a lot more drug. But the other thing they noted was, in the short access animals, self-administration levels, the amount of intake, stays very stable across many, many, many days. Whereas in the long access animals, there's a gradual escalation of intake. And so they argued that the escalation of intake, which of course is one symptom of addiction, if you will, must mean that having long access, again, has changed brain in some way to produce this addiction-like behavior, and that this kind of model then may help us better capture what's going on or differentiate the difference between sort of recreational casual patterns of drug use versus addictive patterns of drug use. Now, with long access models, and I just want to impress on everyone, it's probably, as again, the most widely used model out there today. And it focuses on the amount of drug exposure. And this was stated very explicitly by Sir Jamed when he says addiction-causing neuropathological processes can be set in motion only when rats expose themselves sufficiently to cross the threshold for addiction. That is, there's a minimum level of drug exposure that's necessary to produce changes in brain that lead to addiction-like behavior. So given that as backdrop, what I'm going to argue today is, in fact, our current self-administration models are actually not very good for studying the changes in brain and behavior that take place in the transition to addiction. And I'm going to focus on two shortcomings of our present models. One is they don't reflect the temporal pattern of drug use in humans as they transition to addiction. That's in pharmacology called pharmacokinetics. And it turns out time matters. And the second one is all self-administration models require animals to make the same action, one lever press or a nose poke, again and again and again, hundreds or thousands of times to procure drug. And I'd argue that doesn't characterize the behavior of addicts. And it turns out that matters too. And I'm just going to give you examples of that. Caveat, the studies I'm going to talk about focus on cocaine. We'll see how well it applies, these principles apply to other drugs. So first, temporal pattern. Now, when you do drug self-administration studies, the animal's put into the box, and it can press the lever or poke its nose into a hole to get drug. And when they do that, what they do is they load up drug, they take the brain levels of drug to a preferred level, and then they hold it relatively steady for however long you leave them in there, for 2 hours under a short access condition or 6 hours under a long access condition. People, though, people that use cocaine don't take their brain levels of cocaine to a certain level and maintain it at a very high level for long periods of time. You just don't do that. What people tend to do is take drugs intermittently. They take drug intermittently, not only some days they take drugs and other days they don't take drugs, but even within a bout of use, they tend to take drugs in ways that results in the brain levels of drug going up and then falling back down. That's highlighted in this quote that I give here, that cocaine users wait between episodes of use. And the reason is, makes sense if you think of it. If you take drug and raise your brain levels of cocaine, and you take your next dose when it's already high, you just don't get much of effect with that second dose. The real euphorogenic effect comes from the rapid rise in brain levels, so it has to come back down to rise again. And cocaine users aren't stupid. They learn that this is a better way to take drugs. So the question becomes, does it matter? So Ben Zimmer was a graduate student in Dave Roberts' lab, realizing this about the pattern of human drug use, ask a simple question: does temporal pattern matter? And so they're going to compare short access conditions with long access conditions with what they called an intermittent access self-administration procedure that results in these spiking brain levels of drug. Okay? And they ask a very simple question: does experience with these different self-administration procedures, do they differ in terms of how they change or enhance subsequent motivation for drug? Of course, pathological motivation for drug is a hallmark of addiction. Now, when you look at each total intake, that is the intake each day, short access animals here, of course, take much, much less drug on a daily basis than long access. That's the nature of the difference between the two of them. Intermittent access on animals, on the other hand, take about the same amount of drug as short access animals. And it was supposed with long access models that that large amount of drug is what's critical for producing addiction-like behavior. But what they found when they measured motivation for cocaine was, yes, long access produces greater motivation for cocaine than past experience with short access, but you get even higher motivation for cocaine if in the past you've had experience with intermittent access. What that says is that when it comes to producing an increase in motivation for cocaine, the pattern of intake is probably more important than the total amount of drug consumed. And what this says is that the ability of stimuli, like drugs, or even other stimuli to change your brain is very much dependent on the temporal pattern with which you experience those stimuli, and drugs probably no exception to that. Alex Kawa in my lab, he's a graduate student in my lab presently, wanted to pursue these findings and ask how does motivation for cocaine change during a period of intermittent access self-administration. Zimmer did it, the self-administration, and it didn't measure what happened during the self-administration experience. And so what Alex did was train animals to self-administer cocaine, measured motivation for cocaine at baseline, and he's using behavioral economic procedures that generate demand curves that allow you to assess the willingness of animals to work for drugs, what's called Pmax, the maximum price animals are willing to pay, or alpha, which is elasticity of the demand curve, and so on. So it's a behavioral economic measure. So he measured that at baseline, and then every 12 days during intermittent access self-administration experience. First thing he found was intermittent access self-administration experience results in escalation of cocaine intake. So you don't need lots of drugs to see escalation of cocaine intake. And when you use these behavioral economic measures like Pmax and alpha or so on, which are measures of motivation for drug or max charge, that's sort of how willing you are to keep taking drug when you're going to get punished, in this case shock for doing it. What you see is a progressive increase in motivation for drug, what we would call incentive sensitization. They will endure a larger electrical charge to get their drug, and they're more motivated to do it in terms of the maximum price and effort that they're willing to pay. So I'm not showing you all the data, but basically what it seems very clear now is that intermittent access cocaine self-administration produces addiction-like behavior by all the measures that are used in the field. Things like escalation of intake, progressive increase in motivation for drug, more persistent drug taking in the face of adverse consequences. You get very robust reinstatement or relapse kind of behaviors, and so on. So when you go back and think about the assumptions underlying long access models, that is, you need a certain amount of drug before you'll become an addict, these kinds of studies suggest that's simply not true. The pattern with which, the routes and patterns with which you take drug really, really matter and make a big difference whether you'll make this transition from what you can think of as casual or recreational patterns of drug use to addiction. Now, why might that be? We don't really know why it is, because there's basically no neurobiological studies on either, well, there's lots on long access, but nothing, almost nothing on intermittent access. The one study that's been done looking at dopamine function has showed that long access and intermittent access actually produce opposite effects. One produces tolerance and one produces sensitization. Now, if you're in a situation where you have two models that purport to be models of the same thing, and they do the opposite things in terms of brain function, you got a problem. And I think the field is faced with that kind of problem now. That is, these two different modes of allowing animals to take drugs produce very different effects and are probably producing quite different neurobiological effects. And so if we're going to seek mechanism, what is it you want to seek mechanism for? Okay, so that's the first shortcoming I talked about, was temporal pattern. The second problem I see with self-administration models as we use them today is that it requires animals to make the same action over and over and over again to procure drugs. And indeed, in defining addiction, the Oxford English Dictionary states that it matters little whether one speaks of the opium habit, the opium disease, or the opium addiction. But is that true? Is addiction equivalent to habit? You have to first think of what you mean by habit. And in psychology, habit refers to very specific patterns of behavior that are controlled by stimulus response associations that have a variety of defining characteristics. They're performed relatively automatically, often outside of conscious awareness in a very stereotyped, rigid kind of fashion. Habits. And indeed, drug self-administration studies support the notion of addiction as a habit. Because although when animals first learn to self-administer drugs, their behavior is voluntary and controlled by and goal-directed, as they make those same actions again and again and again, day after day, there's a transition from voluntary goal-directed behavior to behavior that is increasingly elicited as stimulus response habits, as argued here by Barry Everett. And that's led to a lot of attention in the field to try to understand what changes in brain are necessary for the transition from voluntary goal-directed behavior to habits, with habits being thought to be reflective of this transition to addiction, if you will. And this kind of argument has been argued for a number of years now by the Cambridge group in particular. But does this characterize addiction? I put up this diagram just to illustrate. This is a paper describing daily life on the street of a heroin user. And they point out that the main problem in addiction, if you wake up in the morning and you don't have drugs, what do you do to get drugs if you're an addict? And as they point out here, you have to always be on the move. Your behavior has to be flexible. You have to solve problems. You have to hustle. You have to figure out where you're going to buy the drug, where you're going to take the drug, avoid the police, and so on. None of those behaviors that are involved in procuring drugs can, by any stretch of the imagination, ever be construed as being habit. These are not habits. Habits are performing the same action again and again because it worked in the past. I would argue that the appearance, or it's not even the appearance, the development of SR habits in drug self-administration studies is an artifact of the way we do drug self-administration studies, which require animals for hundreds and hundreds or thousands of times to make exactly the same action. That results in habits. So habits indeed do develop, SR habits do develop in drug self-administration studies. But I would argue that doesn't characterize what's going on in people. So Brian Singer, when he was a postdoc in the lab, wanted to ask whether habits are necessary, in fact, for the development of these addiction-like behaviors that I've talked about. And so what he did was to develop a self-administration procedure that precludes the development of habits. Habits can't develop. We called this the puzzle self-administration procedure. And in it, when the animal's put in the box, there's 3 manipulandum, a lever, a nose poke hole, and a wheel. And when the animal goes in, it has to solve a puzzle. It's going to have to make a certain number of responses on 2 of the 3 manipulanda before it gets access to another lever which will allow it to take drug on that intermittent access schedule. So every day the animal comes in and there's a brand new puzzle. So every day it has to solve a new puzzle to get drugs, okay? Which is like the addict waking up in the morning. Every day it has to solve a new problem, a new puzzle to procure drugs, to be able to take drugs. Now, with this procedure, it's actually quite hard for the animals. So on this particular form of the puzzle, they had to do 4 lever presses, and then they'd get a tone if it was correct, and then 2 wheel turns, and then they'd get access to the drug. But if they do anything else, they make any mistake, the whole thing resets and they have to start again. And so it's very, very difficult. They have to figure out what went wrong, because there's no signal that anything went wrong. They just didn't get that tone. Rats do work very hard at this puzzle. The puzzle's getting progressively difficult across the 20 days of self-administration, and they continue to work very hard at it, looking at % correct responses, and they're improving on puzzle solving during the day. But if you look at the % correct, they never get better than about 35 to 45% correct. And that's important because it means responding never has an opportunity to become automated or habitual. They're continually having to restart. Oh, what did I do wrong? And restart the thing until they can get it right and get access to the drug. They also become increasingly motivated to work for the drug. Even though the puzzle's getting harder across these 20 sessions, they're working harder and harder at it. They're more motivated to work at it based on the rate at which they're trying to solve the puzzle, at least the rate at which they're making the responses. And importantly, if we omit that tone which guided their behavior completely falls apart. And what that tells you is that seeking behavior remains sensitive to its consequences, which is a definition of a behavior that's not an SR habit behavior. So it's more evidence that this is not being mediated by any kind of SR habits. So what does their drug self-administration look like? It looks pretty much like when we did it without the puzzle. We see escalation of intake, a symptom of addiction. And when we look at these different criteria in terms of motivation for drug, continued drug seeking in the face of an adverse consequence, a progressive increase in motivation for drug, you see that in animals self-administering on a procedure where there's absolutely no opportunity for a transition of behavior to being controlled by SR habits. And it's particularly strong in these animals that reach a number of criteria for addiction. So the conclusion here is that neither the development of SR habits, and I didn't tell you the data, but you don't get this transfer of control from the ventral to the dorsal striatum, which typifies SR habits. But neither of these seem to be necessary for the development of addiction-like behavior. So in conclusion, what I'm arguing is that the development of addiction-like behavior in rats, at least self-administering cocaine, doesn't require the ingestion of large amounts of the drug, which is associated with long access procedures. It doesn't require SR habits to see the development of these addiction-like behaviors. And time matters. That is, the intermittent patterns of cocaine use seem to be especially effective in producing high motivation for drug and a transition to animals showing this addiction-like behavior. And so going back to Alex's paper where we quoted Box, yes, all models are wrong and some models are useful. And I think it's going to be very important for the field to determine as best we can which animal models are most useful and for what purpose. Which, again, I think means going back and really considering the behavior. What kinds of behavioral models are we trying to use to model what? And that can be problematic because I can guarantee you, you won't get a grant to be able to just do behavioral work. To be able to do that, you have to have the neuroscience as well, which means you have to pick your model before you actually know what your model's good for. But that's my little bugaboo. Just in case you think this is something just to do with the field of neurobiology, the neurobiology of addiction, it's not. So I put up this slide, a paper by Greg Quirk, who's very well known in fear conditioning literature. He's worked for decades on fear conditioning, and he published a paper where he accuses himself and all his colleagues in fear conditioning of having tunnel vision. Because what they did was pick one simple model 25, 30 years ago, and they have indeed been very successful in terms of looking for the mechanism that mediates freezing when animals are given a tone that was previously paired with shock as a model for studying addiction. What they're starting to realize is what you have is a mechanism for freezing, but probably not for fear at all. And if you use any other procedure for looking at fear conditioning, you get a different answer in terms of mechanism. And so it's like back to the drawing board in terms of what models you're going to use. So this tendency to develop this tunnel vision because you have a great procedure that gives you results, I think is a shortcoming in the field that we need to overcome. And spend a little bit more time thinking about what kinds of procedures we're using in neuroscience to model what we're modeling. And the last quote, I'm into quotes these days, so I'm giving you a quote here by John O'Keefe and Lynn Nadell. John O'Keefe won the Nobel Prize a few years ago for their work on hippocampus as a cognitive map. And it goes with the cart before the horse. In this, they point out before you go searching down amongst the nooks and crannies, you have to first find the mountains. Now I'm going to interpret that to mean the mountains are referring to the behavioral psychological process for which you're seeking a mechanism. I also put this book up because 1978 was the year I came to the University of Michigan, so it has fond memory for me. So I'd just like to close by thanking Alex and Brian, who did the work from my lab on the puzzle procedure as well as the intermittent access procedure, and I'm happy to answer any questions. Thank you. I'll bring a microphone down. And another one back there.
Sorry, am I on? Yep. I'm a movement person, physical therapist. I was married to a psychiatrist. And I was wondering, I have a question about restless legs. Is that caused by long use of medicines and drugs too, or is it something different? And also, if a person has brain trauma, serious stuff like in the military, well, the pathways are quite a bit up there in the movement side. I guess I'll just stick with the first question.
Many different kinds of insults to the brain, if you will, and you can think of drug use as an insult to the brain, can change, all kinds of behaviors, including various kinds of motor performance kinds of behaviors. So yes, indeed, that can be the case. And there's a whole, field or subfield within the field that looks for the kinds of risk factors you might get in terms of susceptibility to addiction after things like traumatic brain injury, exposure to high levels of stress, particularly in war theaters, and so on and so on. So that's another huge, huge field. There are many, many environmental factors that change the brain in the ways that can change susceptibility to addiction.
Does your research have any application for addictive drugs that humans take? And I'm thinking of benzodiazepines, which have subsequently been found to produce or lead to dementia.
So in terms of drug self-administration models, as I said at the very start, essentially any drug that people will take, other than hallucinogens, and that's a different story, animals will take. So there are many self-administration studies on drugs like benzodiazepines trying to understand how they influence in the brain. And another big question in the field, of course, is the path to addiction the same or different for different drugs? I'm focusing here primarily on cocaine. I put that caveat in on purpose. Opiates, benzodiazepines, alcohol. There's going to be factors that are shared with different drugs of abuse and factors that aren't shared. So, people tend to specialize on their preferred drug, if you will, and you can't always generalize, but again, there are many commonalities. Like, they're all self-administered. They're probably self-administered because of very similar actions on the nervous system. What leads to addiction with different drugs could be quite different.
That was a great talk, but I'm confused at the end because you point out that only a small fraction of humans, when they are taking drugs, become addicted. Yet you showed animal models where it seems, even in the more refined case, that they all seem to have become addicted. Did I get that right?
Well, not completely. So in this, for example, we are actually dividing the animals in those that meet 2 to 3 criteria for addiction, those that meet a few criteria for addiction. And the changes that you see, depending on the measure, are different. So there is individual susceptibility in there as well. It's not that all of the animals are sort of equally developing addiction-like behavior, if you will. The other thing to be said, of course, is they're models. And they don't come close in many respects to modeling what's going on in the human situation. In the human situation, comorbidity for various psychiatric disorders is the norm. We're not modeling that in these kinds of experiments at all. The kinds of social factors that lead or reduce self-administration behavior in people is quite different than if you put an animal that has nothing else to do into an environment where the only thing it has to do is take drugs. So, I mean, in thinking about generalizing to the human condition is so much more complicated that you want to be very careful about doing that, I think. The advantage of the animal model, though, is that it does allow you to ask cause-effective questions about this variable or this factor versus some other in terms of the extent to which these, without all the confounding comorbidity kinds of questions.
Harry, thank you for that great lecture. It was very enjoyable. So my question has to do with how much we can, I guess, trust what has been supposedly established about addiction based on the fact that the models that were used to create addicted animals may not have been appropriately modeling what we need to understand about the way the brain works.
My way of thinking about it is they're telling you something important, but they might not be telling you what was in the discussion section for that paper. And so what you need to do is rethink what the models are doing. So long access models, there's a lot of literature on it. And we know a fair bit about the neurobiology of that. But rather than thinking about long access models as sort of a model of addiction or a model of the transition to addiction, you might consider it a model as what happens in those cases where people really do go on a binge and raise their blood levels. And I mean, that does happen. It's just that it's not the norm, and it's certainly not the norm in the transition to addiction. but it does happen in experienced users. In which case, you get this massive tolerance kind of effect, dopamine systems go down, and so on and so on. And so you may be modeling a particular aspect of addiction. But the tendency is, of course, is to tend to sort of overgeneralize the findings. If we don't overgeneralize, I think it's still telling us a lot and a lot that's important, but not necessarily what the authors thought they were studying in the first place. So that's my charitable view of it.
Harry, my question has to do with, I believe you've been talking about the wow effect, that when a person or a rat gets a wow, this is something unique, that's the effect we should be studying. My question of you is, what is your advice to those that are interested in the molecular mechanisms which you showed on your first slide? What kind of animals should we use? You've got to tell us what kind of an animal gives the really wow effect for the addiction.
If by the wow effect you mean the euphorogenic effect, the subjective pleasurable effect, then that, I think, is very difficult to study in animals. The other wow effect, I mean, Kent Berridge has written a lot on this about motivation or reward kinds of processes being divisible into wanting, liking, and learning kinds of factors. The liking part would be the subjective pleasurable wow kind of thing. But the wanting part of it, that is the motivation for it, which seems separable from how much it's liked, is quite much more amenable, of course, to study in animals. But to study euphorogenic effects of drugs in animals, I don't think we have any good measure of that. I just don't know how do you know how good it feels to a rat? You can know how much they're willing to work for it, how much they want it, but we know in the brain that that's a different thing than the wow. You can measure ultrasonic, you can measure ultrasonic vocalizations. People have done that. So for people who don't know, rats emit low-frequency ultrasonic vocalizations that are saying this is bad, and high 55 kilohertz like ultrasonic vocalization this is good stuff. And you can measure that. Drugs of abuse do produce these good ultrasonic vocalizations. People have touted that as sort of some insight in terms of the subjective effects. But it's still pretty hard to know if those ultrasonic vocalizations are related to Ed's wow or related to motivational kinds of factors. It's very, very hard to separate. And so it's a different thing.
Can I ask one last question?
These animals are adults. They're not adolescent or senescent. I'm thinking about the West Coast and how it's entirely recreational pot, but they don't want strong marijuana in the hands of high school kids or college kids, hopefully, or anyone, but that's my opinion. And let's not forget about seniors who are taking pot after they retire, and they're using medical marijuana, which is much stronger than it was when they tried it in college in the 60s. So, but, there's all the other drugs, and you're dealing with addictive drugs. And
the question about age is an important one. And again, I don't have time to touch on that here, but there are a lot of people interested in studying adolescents. This is all adults. But there are people that study self-administration in adolescence, very little in old age, but in adolescence. And there are a number of studies suggesting that adolescent animals acquire self-administration faster, develop these addiction-like behaviors faster. The brain is much more plastic, at the younger age. So that's a whole subfield about how things like age serve as a risk factor to undergo these drug-induced changes in brain that lead to addiction-like behavior. So that's not something that's ignored. That's something that people are very, very interested in pursuing. How sensitivity of brain to drug-induced change varies as a function of environment, age, sex, gonadal hormone status, all kinds of factors. That the field looks at all of those sorts of things. And they all influence what the drug does to the brain.